Our next speaker is Elizabeth Cutrone, and she's the Director of Data Science at Precisely. And Precisely is a company focused on delivering up-to-date contextual data to businesses to enhance decisions with location intelligence and consumer insights. So yeah, we're super excited for her to share how she's built a serverless workflow to derive insights on social dynamics in cities. So yeah, as a economic geographer, near and dear to my heart, and very excited to see what you have to share with us today.
All right, great. So thank you again for the introduction. I'm a director of data science at Precisely, which is a leader in data integrity, and one of many things we offer is many different types of location data sets, as well as location intelligence insights, which are kind of tangential to the project I'm going to present today, but certainly related. So please drop me a note if you're at all interested and you think this is valuable. We can talk more about Precisely as well. But for now, I'm going to present a project using New York City taxi data, and I called the results chronotypes, and I think you'll see why. But first, I want to say like a little bit of background information on neighborhoods, which is the element that I tried to understand. These are very valuable geographic units. I think most people have kind of a colloquial understanding of a neighborhood as a subunit of a larger city that has consistent properties within itself in terms of population demographics, dynamics, types of places that are located there, et cetera. Consistent within neighborhoods and are sort of different between distinct adjacent neighborhoods. And understanding this kind of thing has all kinds of great business implications for advertising, for site selection for new businesses or new residential developments, risk analysis, transit planning, all kinds of stuff. And in many cases, there are existing boundaries like zip codes and census blocks, but those things aren't always applicable to relevant use cases. They're really good at what they were designed for. So if you're delivering mail, zip codes are really great, and you probably want those boundaries. But for other applications, they don't work so well. And in many cases, there's consensus on location and names of neighborhoods, but a lot of variance in the way people understand the boundaries kind of socially between these places. So the figure on this slide is an example. It was created by the New York Times a year or so ago. And I remember it being very like buzzy sort of cocktail chatter when they first released it, because I think people love to debate this kind of thing in New York and probably in pretty much every city. But they basically went around and asked a ton of people, what neighborhood do you live in? And what do you think are the streets that define the boundaries of that neighborhood? And from the shading between all the colors, you can see there's a huge variance in where people think those boundaries are. And it's a question I've always been kind of interested in my work at Precisely. I've gotten to deal with lots of different kinds of location data sets. So I've always been kind of interested in how different kinds of location data can inform these boundaries and how we can sort of determine them in a more data-driven way. So for this project, I decided to start trying to understand neighborhoods through New York City taxi data. And part of the reason I was interested in taxi data, aside from it being open and freely available, is that it's got precise locations of pickups and drop-offs for every single taxi journey over a period of time. It's also got dynamic information, so there are timestamps attached to those journeys. And it represents a huge segment of human and or consumer behavior. So looking at this data, we can kind of understand patterns of behavior, patterns of movement through the city that actually functionally define neighborhoods in terms of where people actually go, rather than a sort of municipal boundary like a census block or someone's personal idea of what a neighborhood is. It's also similar, I should say, to many data sets that I've worked with at Precisely. So I'll give one more quick shout out that if you find this interesting and valuable, please give me a shout. So I'll just quickly review how I approach this problem, and then I'll jump over to my Workbench so you can see how it works. So I binned the taxi data by H3 hexagon and hour of day. So this gives you a single vector with a length of 24 for every single hexagon in the city. And this lets you compare pairs of hexagons based on these vectors. I'll show how I did that. Cosine similarity is sort of the obvious and immediate choice, but I tried a couple of different versions. And then I continued by using one location as sort of a reference point and looking at the similarity of all the hexes across the city to that individual location, and kind of explored by looking around and choosing more reference points. So I'll jump over to my workbench and show you how I address this. So I defined a UDF, which first loads the taxi data. There's actually a pre-made public UDF that loads in this data and bins it by hour and hex. I binned it again into larger day parts to sort of just reduce the dimensionality a little bit. And then normalized each hexagon so that all the counts or all the elements of the vectors add up to 1. And here's where I select a reference hexagon. The location for this hexagon is passed into the UDF as a set of parameters. And then you simply compare that with all of the other hexagons. As I was saying before, one thing I looked at was cosine similarity. I also tried this other metric called Jensen-Shannon distance, which I'm not going to talk too much about because I actually don't think it made a material difference in the results in this particular case. But I thought it was an interesting metric to try, and I thought it was a better fit logically for this particular problem. So now you've got a similarity metric for every single hex in this map. And that's roughly what's shown over there. But one additional thing that I will mention is I added a bit of smoothing to this map. So just whenever you calculate a metric across a bunch of tiny individual pixels, of course, you end up with some really complex borders and kind of speckly areas. So smoothing takes care of a lot of that. And for time, I won't get into too much detail. I'll just say that it's incredibly easy with the H3 framework because you have immediate access to each hexagon and all of its neighbors and all of the parent hexagons, which is like the next lowest resolution hex. So that's really all you need to do smoothing. You just have to take the right average of all of those things in the right intelligent way. So that becomes very easy. Then finally, I sort of clipped off the least interesting, least similar hexagons to sort of narrow this view to the most dynamic and interesting range. And what you get is this map of similarity values with respect to a reference point that is somewhere down here. Someone's going to have to fact check me, but it's the coordinates of New York City Hall. So that's a municipal building, which probably gives you an idea of roughly the hours of day that are most popular for taxi pickups. And what I wanted to do to make this really interesting was to compare this to an additional reference point for a neighborhood that I already know would be very different from this. And there are many ways of doing this. Maybe the most elegant way would be to define a new function that calls this UDF and calculates two different similarity values and plots them all. Personally, I found it much easier and much more conducive to my workflow, since I'm just exploring this data now, to actually just make a carbon copy of this UDF and pass in a different set of default parameters. So that's what I did, and then you just have to turn on this layer, and immediately I can start exploring the results in the map. So the location that I chose as a reference here is someplace down here in the Lower East Side, which if you've spent time in New York, you probably know is really a nightlife hub. So there's tons of bars, restaurants, and clubs, all kinds of things where you can imagine the taxi traffic would vary a lot compared with City Hall. So I thought this was a really cool result. One of the things I really appreciated is that it highlights neighborhoods that are disjoint from the Lower East Side and even very far away. So here's the Hell's Kitchen neighborhood, up here is West Harlem. And even though they're far away, through this metric, you can interpret that there's actually a lot of similarities between these two disjoint places. One more thing that I really love is, even though I applied some smoothing to make sure that the boundaries didn't get too complex, there's some very small green blobs that kind of stand out, and they are representative. They actually present signal and not noise. So this one, for example, is located over the Koreatown neighborhood, which is in fact very small and is in fact right around this location. So I thought that was a really cool result. Jumping over to the app builder, I did a little more analysis of those results shown in the graphs here. So one thing I did was to look at the cumulative count of hexagons in each case across that similarity value. And I think this is useful because for almost any use case, you'll probably want to narrow down to whatever is the most relevant range of hexagons and cut out the rest. So if you want the most similar, most important ones, you want to look at like the top of this curve where it flattens out, or maybe you're interested in the dynamic range where the slope is the greatest.
Very cool.
Finally, the last thing I did was, I can assume I'm running out of time by that comment, but I quickly also looked at a histogram of the taxi pickups over the most and least similar hexagons for each particular reference point. So it's just a nice confirmation that we're actually picking up on two different groups. And I think also points towards some interesting follow-ups in terms of discriminability, because even though you can see that these distributions are pretty different, there's enough overlap that if you chose one item, one hex, or one taxi journey, or whatever, it would actually be pretty hard to figure out which distribution it came from. So, of course, as you might imagine, as is probably the case with any machine learning model, if you added a bunch of features to this, I think you would see a lot more interesting results, and you could try to optimize that discriminability.